These are the lesson activities for section 3.2 for differential equations. Okay, we're given a system of linear differential equations. I'm going to translate this just for practice. This says that x prime, y prime equals 3, 2, 0, negative 2 times x, y, which means x prime is 3x plus 2y, and y prime is 0x minus 2y. Okay, find the eigenvalues for the system. So that is done by calculating the determinant of a minus lambda I and setting it equal to 0. Okay, so the determinant of a minus lambda I, A is the coefficient matrix, 3, 2, 0, negative 2. So I need the determinant of a minus lambda I. That would be 3 minus lambda, 2, 0, and negative 2 minus lambda. So to calculate the determinant, we do A times D minus B times C. So that comes out to 3 minus lambda times negative 2 minus lambda minus 2 times 0, and we set that equal to 0 and solve it. So that whole term is just a 0, so we have 3 minus lambda times negative 2 minus lambda equals 0. It's nice that this is already in factored form, so we get lambda equals 3 and negative 2 are our two eigenvalues. Find the eigenvectors associated with each eigenvalue. So to find eigenvectors, we have to solve a v equals lambda v, and we do this for each lambda. So a is 3, 2, 0, negative 2 times an unknown vector xy equals lambda, which is a 3, times xy. Translate this to equations and we get 3x plus 2y equals 3x and negative 2y equals 3y. Both of these say that y is 0. Y has to be 0. So you can pick any vector that has a y entry of 0. So it would be like 1, 0 would be a nice easy one. There are infinitely many. You could do 2, 0 or 5, 0 or negative 10, 0. Any vector that satisfies the y equals 0 is an eigenvector associated with lambda equals 3. Okay, so we do the same process for lambda equals negative 2. We have 3, 0, 2, negative 2 equals negative 2 times xy. Sorry, I forgot the xy here. Okay, so this says 3x plus 2y equals negative 2x and negative 2y equals negative 2y. That second equation tells us nothing. Any y you put in will make it true, so we'll just ignore that. So this first equation says that 5x equals negative 2y, and you just need any xy pair that would make this true. So I like to solve for one of the variables. Maybe I'll solve for y. So you get y equals negative 5 halves times x. And then you pick any xy that makes that true. So you choose an x. I like to choose an x value that will make it so I don't have, y does not come out with a fraction. So I might choose x is 2. And then y would end up being negative 5. Any xy pair that makes that equation true forms an eigenvector. So 2, negative 5 is not the only possible one. Okay, knowing the eigenvectors, graph the straight line solution curves that appear on the vector field and mark arrows showing the direction. Okay, so 1, 0 is this point right here. 1, 0. So here's my straight line solution. It's the line that goes through the origin and the point 1, 0. And it's associated with lambda equals 3, which is positive, which means we put arrows going away from the origin. So there's one straight line solution. And then 2, negative 5 is this point right here. and I'm going to do the line that connects that point to the origin. And that eigenvector, that line of eigenvectors, is associated with a negative lambda, -2, so I have arrows that point in towards the origin. Give the formula for the particular solution to this system that corresponds to each eigenvalue and its associated eigenvector. So for every eigenvalue eigenvector pair, we have a solution of the form e to the lambda t v. So y1 would be e to the 3t times the associated eigenvector, which was 1, 0. And y2 would be e to the -2t times the associated eigenvector, which is 2, -5. There we go. There's our two particular solutions. The system had two distinct eigenvalues, 3 and -2, so which means we can write the general solution by taking a linear combination of our two particular solutions. So y general would be k1 e to the 3t times 1, 0 plus k2 e to the -2t times 2, -5. Lastly, we want to find the particular solution to the system that satisfies the given initial condition. So y of 0 is k1 e to the 3t, that would be e to the 0, which is 1, times 1, 0, plus k2 e to the 0 is 1 times 2, -5. Supposed to give me 6, -5. So I can break this out into two separate equations. The first entry says k1 plus 2k2 is 6. And my second entry says that 0k1 minus 5k2 equals -5. So that's nice because that means that k2 is 1. And then I can put the 1 into the other equation. So I have k1 plus 2 equals 6. So k1 is 4. So my final particular solution would be y equals k1, which is 4, e to the 3t times 1, 0, plus k2, which is a 1, e to the -2t times 2, -5. Okay, question 2. Consider the second order equation y double prime equals 5 plus 5y prime plus 6y equals 0. Write this as a first order linear system of equations. So you always do that by starting with y prime equals v, and then v prime is y double prime. So I solve this equation for y double prime, and I get negative 6y minus 5y prime. But y double prime is the same thing as v prime. And then we have negative 6y minus 5y prime, which we have defined to be v. So v prime is negative 6y minus 5v. Write the system in matrix notation. So we've got y prime, v prime equals, and then I have a matrix times yv. So my y prime equation is y prime equals v. So 0y is 1v. And v prime is negative 6y's and negative 5v's. Find the general solution to the system using eigenvalues and eigenvectors. So we start by looking for eigenvalues. So I calculate the determinant of a minus lambda I. So this would be negative lambda 1, negative 6, negative 5 minus lambda. That is negative lambda times negative 5 minus lambda minus 1 times negative 6. So that's 5 lambda plus lambda squared plus 6, which is, to write that in the descending powers, we have lambda squared plus 5 lambda plus 6, which we can factor to lambda plus 3 times lambda plus 2, which is 0. We set that equal to 0 and solve, and we get lambda equals negative 3 and negative 2. Okay, now I need eigenvectors to go with each of these, so I have to solve AV equals lambda V for each eigenvalue. So A is 0, negative 6, 1, negative 5, times an unknown vector xy has to equal negative 3, my first eigenvalue, times xy. So this says 0x plus 1y equals negative 3x, and negative 6x minus 5y equals negative 3y. So negative 5y equals, oops. If I were to solve this for y, I would get negative 5. Add 3y to both sides, and I get negative 2y equals 6x. So this equation and this equation are equivalent. So I just need to pick an x and get the y. I'm going to pick 1 for x, then negative 3 would be y. So there's one eigenvector for lambda equals negative 3. And then I do it again for lambda equals negative 2. So I have 0, negative 6, 1, negative 5 times xy equals negative 2 xy. So this says y equals negative 2x. The second equation is going to be redundant. An xy pair that makes that equation true would be 1, negative 2. This is for lambda equals negative 2. Okay, so the general solution to the system is y and v. I need a y and a v. So I think I'm going to write it in vector form since that's how we learned it, and then I'll break it out into the y and the v. All right, so my general solution is y in vector form is k1 times particular solution 1, which is e to the lambda t v, plus k2 times particular solution number 2, which is e to the other lambda t times the associated eigenvector. Okay, so now what we do is we break this out into the y and the v. Y is the first entry and v is the second entry according to how I defined the system. Y is on top, v is on the bottom. Okay, so y is going to be k1 e to the negative 3t plus k2 e to the negative 2t. And then v is the second entry, so I get negative 3 k1 e to the negative 3t minus 2k2 e to the negative 2t. What is the general solution to the second order ODE? That's just the y, right? So we don't, when you're solving a second order ODE, solving the system is equivalent, but it gives you a second piece of the solution that you're not asked for a second order. So it's just the y from above. We'll just copy it down.